Here we have a semicircular lamina centered at the origin. Its diameter is along the x-axis. That means its center of mass by symmetry must lie along the y-axis. So at least we know that x bar is 0. To get y bar, we need to get moments of mass elements about the x-axis. So the distance of each mass element to the x-axis will be y. It is best to take our mass elements as thin horizontal strips. Again, these are not point masses, but the calculation will still work out. The thickness of each mass element must be delta y, because the thickness is in the vertical direction. Suppose xy is a point on the circle. Well, half the width of this strip then will be x. So we are going to approximate this strip as a rectangle, and the approximation gets better, of course, as delta y goes to 0. So both sides of the rectangle will have the same length as delta y goes to 0. We need the mass of this strip. To get the mass, we need the area. Well, one side of it is x plus x, which is 2x units long. We take x to be the positive number here now, point on part of the circle that's in the positive quadrant. So it's 2x multiplied by delta y. So that's the area of the strip. Suppose rho is the mass per unit area of the semicircular lamina. Well, if we multiply the area of the strip by rho, we have the mass of this strip. To get the moment of this strip about the x-axis, we must multiply the mass of the strip by the perpendicular distance of it to the x-axis. That's y. That's the y value of this point here. But since we're dealing with a circle centered at the origin, with a radius of a, so this here is a, its equation is x squared plus y squared equals a squared. So this is the equation of the circle. It essentially comes from Pythagoras' theorem. Just as a reminder, this distance is x, this distance is y for any point xy on the circle, say in this quadrant here, and the hypotenuse is equal to the radius, which is a. So x squared plus y squared equals a squared. Now here is y in terms of x, but actually we need x in terms of y. Because the thickness of the strip is delta y. So when we take the sum, delta y will come into the sum of all the moments, and delta y becomes dy as we take the limit of the sums. So we're integrating with respect to y. So that means we will want x as a function of y. So if we go back to what we had before, the moment of the strip about the x-axis is given by this here, and we sum all those strips, y equals 0 to a, that gives us an approximation to the sum of the moments of the strips about the x-axis. So we're summing from y equals 0, that would be this point here, to y equals a, that's this point here. The radius of the circle is a. So the first strip will be down here, it will have thickness delta y, and the last strip will be right up here. Again, the thickness of all the strips is delta y. So we're summing from y equals 0 to y equals a, and we can make this approximation exact by taking the limit as delta y goes to 0. So we replace delta y with dy. So that's why we need to have the integrand in terms of y, since we're integrating with respect to y. So we need to replace x with root y squared minus a squared, x the subject of the equation of the circle. So the 2 rho is just a constant that can come outside. So what we need to do is write what's inside the square root sign as a single term. Actually it says u squared here, this should be u. So we let u equal a squared minus y squared. So differentiating u with respect to y, a squared is a constant, so we get minus 2y. And from that we get dy equals du divided by minus 2y. So we just interchange these to get dy. So now we rewrite our integral. So we have the 2 rho that can come out. We have a y. We have the square root of u. So we plug in for u. And then we have dy, which is du over minus 2y. You can see that the y's cancel. So the integrand just involves u. That's what we want. And it's a simple function to integrate. We're integrating u to the power of a half with respect to u. Now, as for the limits, let's look at the lower limit, y equals 0. Well, But when y is naught, we see that u is equal to a squared. The upper limit y equals a, so if we plug a in for y, we get u equals a squared minus a squared, which is naught. I forgot to cancel the 2's here, and we have this minus sign coming out. Integrating u to the half gives us 2/3 u to the power of 3 over 2. Plug 0 in for the upper limit and we get 0. Then we have minus sign, and then plug in the lower limit a squared. So we've a squared to the power of 3 over 2. That's a to the power of 2 times 3 over 2. That's a to the power of 3. So we end up at 2 rho a cubed over 3. To get y bar, we could just divide this thing by the mass of the semicircle. The area of a circle is pi times the radius squared, so half pi a squared is the area, and we multiply that by rho to get its mass. So we could just divide this by the mass. So you see the rho's cancel out. One of the a's, a squared cancels out here, so we have a on top here. Multiply both sides by 2 to get 4 on top. Divide both sides by pi to get 3 pi in the denominator. So we saw that y bar is 4 divided by 4 over 3 pi multiplied by the radius. So here is 4 over 3 pi. So you can see it's about 0.42 times the radius. So y bar is a little under halfways along this line here, because this is a here, of course. So 0.42a is about here somewhere. It's no surprise that the center of mass is less than halfways between this point and this point here, since more of the mass of the lamina is below this point. Well, I mean, if the center of mass was exactly 0.5 times the radius, then we'd have more mass below than above.